Let's take a look at this problem. The data to the right represent number of days of the growing season over the last 10 years in a certain geographic area. Is known data normally distributed and that S is equal to 21.64. So there's, looks like there's 10. Corresponds to what they said with 10 years. So that means N is 10. And they've already calculated S for us, sample standard deviation. And that's 21.64. Okay. Using these values of simple random sample, construct a 98% confidence interval. Now here's where you have to read the problem close. 98% confidence interval for the population standard deviation. Population standard deviation. We've got two formulas. Two sets of formulas. Got confidence interval for population standard deviation, which is this one. And we got population variance, which is this one. So you may have a mixture of both types in here. Well, the one we're wanting is the population standard deviation, so this is the one we want. Well, let's see what they're asking for. They're asking for N, S. Well, we got N, we got S. They're asking for these right here. Now, this is not the same notation that the book uses, but I like these notations better. So, we got 98% confidence interval. This should be drawn as a chi-square, but it doesn't matter the shape. I usually draw these as bell-shaped more, just to really easily write it. And these add up to 100%, so if I put 98% in the middle, I'm putting 2% in the tails, and splitting it up, I put 1% in each tail. There we go. Now this one right here, this is my left chi-square, and this one is my right chi-square. Now this is not the second power, this is just notation. So to find these, we need a degree of freedom. Now degree of freedom is N minus 1, so there's always one less than N. So we got 10 minus 1, or 9. Okay, now let's go to our appendix. If I come down here and I click chapter contents, then scroll down, you'll see appendix A, and then click appendix A there. I have to do this in Chrome. It doesn't work in IE for me, but a lot of things don't work in IE for me. Let's see, how do I go to the next page? There it is. Next page. Next page. I actually think I want to go through A-12, but I'm not really sure, so. No. A-14. Okay. Now I notice over on the left says degrees of freedom. We just said in this problem our degree of freedom is 9. So we're going to go look at this row that corresponds with 9. Now across the top it tells you what to do. It says area to the right of the critical value. Let's find the right chi-square first. So I'm working with this line. The area to the right of that is this 0.01. So I'm going to look up 0.01, which is clear over here, and I go down to 9, and that tells me it's 21.666. Now I'm going to look at my left chi-square. Look at this line right here. Now look to the area to the right of it, which is a 0.98 plus a 0.01, which is 0.99. So I'm looking at a column with 0.99, I go down degree of freedom of 9, and I get 2.088. Okay, back to our formula. Lower bound. Lower bound is equal to square root N minus 1 S squared over the right chi-square. Our upper bound will be N minus 1 times S squared over my left chi-square. Okay, so let's plug in our values. N was 10, so we got 10 minus 1. S was 21.64 squared over my right chi-square, which is 21.36, and I'll plug that in the calculator here in a minute. Now I do the same thing with this one. So I got 10 minus 1 s, which is 21.64 squared, divided by left chi-square, which is 2.088. Okay, so we've got square root second x squared. 10 minus 1, I'll go ahead and just put 9 in. 9 times 21.64 squared divided by 21.666. Enter. Probably 2 decimal places if I had to guess. That's what a lot of them go to, but I better not guess. 2 decimal places. Okay, so it's 13.95. Now, other one. Now, I'm going to do second x squared. You could also do second enter and change to whatever values, but I'll type it in again. Times 21.64 squared divided by 2.088. And that gives us 44.93. And that's where they get those values there. So that's how you'd work a confidence interval for the population standard deviation problem.